Hello and welcome to the lecture for Chapter 1 of OpenStax Astronomy. This chapter is titled Science and the Universe, A Brief Tour, as we can see right here. This is a very introductory chapter. We're not going to get into a lot of details. There's going to be no kind of cohesive big message of this chapter. It's just a brief, fun introduction to the topic of astronomy. So let's get to it. All right. So here we're looking at a collision of galaxies to give you the idea of the scale of the universe. Right? So it says here these are two interacting islands of stars, and they're so far away that light takes hundreds of millions of years to reach us on Earth. That means that these galaxies are located hundreds of millions of light years away. That means the light takes hundreds of millions of years to get here, which means when we look at this picture, we're looking back hundreds of millions of years into time. Okay? This light was created when dinosaurs roamed the Earth. Furthermore, hundreds of millions of light years corresponds to hundreds of millions of tens of trillions of kilometers, because there are almost 10 trillion kilometers in a light year. Okay? A kilometer being a little bit less than a mile, right? Okay, so the unbelievable scale of the galactic universe, a universe populated by many, many galaxies, is mind-boggling. But what is a galaxy itself? Because, of course, we live in the Milky Way, okay? Well, I want you to hold on to that idea, all right? Coming much closer to home, but still foreign and awe-inspiring, we're looking here at a picture of Mars. This image of Mars is centered on the Valles Marineris, the Mariner Valley, a complex of canyons which is as long as the United States is wide, right? So it's this stretch across the Martian surface, right? Mars is smaller than Earth, but it has huge valleys, giant volcanoes, all evidence of past geological activity, but currently the planet appears to be quite inert, quite dead. No atmosphere unlike Earth, right? So many mysteries there. Now, we're not going to delve into the mysteries of the planets, the gas giants here in our solar system, the moons of Jupiter and Saturn. That's a different course, and that's a wonderful thing to talk about. That's where you could investigate Pluto and planets like planetoids like Pluto. Instead, in this class, after we get through this introduction to astronomy, we're going to move more into this big picture. What is the whole universe? How do we understand things on the scale of the Big Bang? All right, here we're looking at something that would be populated in our own galaxy, in the Milky Way, right? That our solar system, our star, is part of. This is a stellar corpse. This is an exploded star, a star that blew up and left a nebula behind. We observe the remains of a star that was seen to explode in our skies in 1054, right? So less than 1,000 years ago. How do we know that? Well, there's a lot of writings of the supernova, right? People discuss seeing it in the sky, it being visible like a bright new star in the sky for many months. Okay, we have astronomers in 1,000 years ago, so we have astronomers in China, we have astronomers in the Arabian world, we have astronomers in Europe, right? During the European Dark Ages, we have these records of this event that all coincide. Okay? All right, today the remnants is called the Crab Nebula. So nebula means a gas, a cloud of gas in space. And its central region is seen here. Such exploding stars are crucial to the development of life in the universe because they spread out the building blocks of life. Okay? What are those building blocks of life? More on that later when we talk about stellar lives and the life cycle of stars, right? But that's an interesting idea. How is it that stars could ultimately create life? How is it that we ourselves are made of stardust? Here we have another nebula. That's a cloud of dust in space. This beautiful cloud of cosmic raw material, gas and dust, from which new stars and planets are being made. So sometimes we call this a stellar nursery, right? This is the hot gas where stars are being created. This is the Orion Nebula. It's about 1,400 light years away. So compared to hundreds of millions, this is much closer, right, compared to those galaxies. That's because this is within our galaxy, okay? It's a pretty big number. Here we have the number of kilometers, right? And again, the idea there is that we take the number of kilometers in a light year and multiply by 1,400 in order to get this value, okay? So if you wanted to find out how many kilometers are per light year to see if it is about 10 trillion, as I said, well, you would take 1.34 times 10 to the 16, divide it by 1400, and what you should get is something on the order of 10 to the 13. Why 10 to the 13? Because a trillion is 10 to the 12. Just like a billion is 10 to the 9, and a million is 10 to the 6. If you're not familiar with scientific notation, what I'm saying is that's how many zeros there are. So a million is a number followed by 6 zeros. A billion is a number followed by 9 zeros. And a trillion is a number followed by 12 zeros. So this number here, 1.34 times 10 to the 16, is a number followed by 16 zeros. Okay? It's the number of kilometers. Okay? And that's all close, relatively, because that's within our own galaxy. Okay? And our galaxy is a lot bigger than 1,400 light years across. It's about 100,000 light years across. That's the diameter of the disk that is our galaxy. Okay? Here we have a telescope in orbit. Maybe you've heard of the Hubble Space Telescope. Shown here in orbit around Earth, it is one of many astronomical instruments in space. Why do we put astronomical instruments in space? So that our own atmosphere does not interfere with our recordings. When we have an instrument out in the vacuum of space, we can record distant things with no interruption of those signals passing through the atmosphere. Okay? Here we have Earth, right? Yes, home. This image shows the Western Hemisphere as viewed from space, 35,000 kilometers above Earth. All right? So this is out in space, right? It takes a long time to travel 35,000 kilometers to get this far away from Earth. But compare that to the other numbers we saw, the numbers that were 10 to the 16 kilometers, okay? Just to get to a nearby nebula. So just to put it in perspective, right? Nothing's close to our planet. Even other planets in our solar system aren't close to our planet, okay? All right? Here we have the distance between Earth to the Moon, all right? Drawn to scale. This image shows that Earth and the Moon are relatively close. The Moon, right, if we think of the diameter of the Moon, that would be the distance across, right? Diameter, right, just cutting across a sphere, the sphere of the Moon. Well, it would take about 60 moons to get the distance between Earth and the Moon. So if you stack 60 moons on top of each other, you would cover this entire distance, okay? So it takes a couple days to get to the Moon when you send probes to the Moon, right? It took all the moon landings, over a day, over 2 days to get to the Moon, because we are talking about hundreds of thousands of kilometers, okay? However, it is relatively close. Our Moon is quite close. That's why it gives us dramatic tides, okay? And again, better served for another class, so maybe tantalizing you to take another class, is that the Moon has interesting origin stories. There are very interesting theories about how the Moon was created and why it is so close, because it's not typical for planets to have a Moon as close as our Moon is to Earth. All right, here we have the solar system. Do you think this picture is drawn to scale? Not at all, okay? The last one gave you some idea, right? Moon, small spot, Earth small, right? That figure showed very small dots. Here we have large objects, okay? Now, are there scales in this photo or this diagram? Yes, there are, right? So the relative sizes of the planets are to scale. Jupiter is, in fact, this much bigger than Earth, right? So we can see Jupiter is huge. The Sun is this much bigger than Jupiter and unbelievably larger than Earth. You can think about how many Earths would fit inside of the Sun, okay? The spacing is not to scale, okay? The spacing is just showing them lined up. That's all there is to it, okay? We're just lining them up. We're not trying to put anything to scale in terms of the spacing. In fact, the solar system is very spread out. These terrestrial planets are much closer to the Sun, and these planets start to become very spread out from each other. They're not evenly spaced like this. Neptune is the distant edge of the solar system, okay? Much further, many times, tens of times further than Jupiter is from the Sun, all right? Certainly tens of times further than Earth is from the Sun, okay? But their sizes are shown nicely in this figure. All right, here we have a spiral galaxy. This is what our galaxy would look like if we could look at our galaxy, but that's something that we'll never be able to do because the distances are unbelievably large, right? But if we could get a view of our galaxy from above, it would look a lot like this, okay? This galaxy of billions of stars has a catalog number, right? So it doesn't have much of an official name. NGC 1073. But it's thought to be very similar to the Milky Way galaxy in terms of this bar in the middle and these long spiral arms formed of stars. But check out that number, billions of stars. So every single galaxy, an island of stars, a spinning disk composed of stars, has billions of individual stars, our sun being one of those, of course. So when we saw those colliding galaxies in the first picture, each of those colliding galaxies had billions of stars. But those, of course, aren't our galaxy, neither is the one shown here. How many galaxies do you think there are in the universe? Well, it turns out hundreds of billions of galaxies, each of which have billions, often hundreds of billions of stars. Okay? We'll think about that number later. Here's a view of the Milky Way galaxy seen from Earth, because when we look up in a certain direction, we're looking into the plane of the galaxy, right? Because the galaxy is very planar. It's spinning, like I said, like a disk. It's not a cloud, it's more like a spinning disk. So there's a particular direction here with this long exposure photograph. If you look in a particular direction, you're looking into the denser section of our own galaxy. And so it looks like this tendril stretched across the sky of clouds of dust and dense packings of stars. Okay? Within our galaxy, there are clusters. You can kind of see that if you look at this picture of a distant galaxy. The stars are not evenly distributed. Of course, they're located along these arms of the galaxy, and they're clustered into clusters within the arms. All right? So if we look within our own galaxy, we see evidence of those clusters. Here we see a large star cluster that is known by a catalog number, M9. It contains about 250,000 stars, right? So that's a lot, right? But remember, there are billions of stars in the galaxy, right? So this may be a very large cluster of stars, right? Every one of those stars may have many, many planets. But that is just one tiny portion, right? Because you think about, if we have a billion, right, which I told you is 10 to the 9 zeros, and our galaxy has 100 billion stars. Well, 100 times 10 to the 9 is 10 to the 11, because we add 2 zeros. So we have 10 to the 11 stars. Well, 250,000, well, that's about 10 to the 5. Like 100,000 has about 5 zero places if we ignore the 5, right? Well, then we could take that 10 to 11 and divide by 10 to the 5, divide by a star cluster that has about 100,000 stars in it, okay? And what do we get? Well, we would get 10 to the 6, because we lose 5 zeros and we'd have 6 left over. Well, 10 to the 6, of course, is 1,000,000. So that means that although the star cluster is huge, right, composed of so many individual stars, that, well, there could be 1,000,000 such star clusters in our entire galaxy. Think science fiction movies like Star Wars. Think how they have a civilization that's stretched across many stars, and they talk about the planets of each stars, and they're moving from one system to another, right? One star system to another, jumping with, their warp abilities from one star system to another. Well, that entire civilization, like that, this galactic opera of civilizations, could certainly fit in 250,000 stars, right? That could be a huge, stretching interstellar civilization. But there could be 1,000,000 of those in our galaxy, right? There's got to be a lot of aliens out there, right? All right, so back to neighboring galaxies. This image shows both the large Magellanic cloud and the small Magellanic cloud above the telescope of the Atacama Large Millimeter and Submillimeter Array, right? So this is an array of telescopes. Might be not what you thought when you thought of a telescope, but I'll mention that in a second. All right, this is in the Atacama Desert, and that's the name of it, in northern Chile. So we're looking at these big clusters of galaxies, okay? So every one of those little smudges in the sky contains thousands of galaxies. They're clusters, because the galaxies themselves compose a structure that spans the entire cosmos. The cosmos is a name that's given to this idea of the entire universe created in the Big Bang. Okay? Ideas that we will certainly discuss in this class. Well, why do the telescopes look so strange? I wanted to get back to that. It's because they're radio telescopes. These aren't light telescopes, okay? There are a lot of signals in space, a lot of evidence that we can gather that is in the radio spectrum. And we'll talk about the spectrum of light. Radio waves are included in the light spectrum, often called the electromagnetic spectrum. Just light is a term often given to visible electromagnetic radiation, okay? But that's just one type of light. So if we use the term light to compose the entire electromagnetic spectrum, including microwaves and radio waves and X-rays, that's all considered light, okay? Or EM waves, EM standing for electromagnetic, because light is an electromagnetic phenomenon, okay, including the type that we see. All right, here we have the Andromeda Galaxy. This is the galaxy that's our neighbor, our closest galaxy to us. It's about 2 million light years away, so relatively close compared to the colliding ones, which are 100 million light years away. All right. In this image, you can see part of a cluster of galaxies located about 60 million light years away in the constellation of Fornax, right? So you can see that we have, these, you can actually see a spiral on this one. Some of these other galaxies just look like smudges because there's different types. This one clearly looks more like a spiral galaxy. You can see much smaller spiral galaxies, right? So if you have a good telescope, you realize that between the stars, between the bright stars that you see in the sky, there are all the galaxies visible as long as you have a good telescope. All right. So now we're getting into the idea of time in the entirety of the universe from the very beginning to the very end. I wanted to check for one thing. I had there it is. Okay. So the I'll get back to the slide. In fact, I want to show you one more picture first. This is the Andromeda Galaxy again, and I wanted to point out that it would appear quite large if it wasn't so far away and dim. This is the moon in the sky, right? When you look up in the sky, the moon, it's a big object in the sky. It dominates the sky to some effect, right? Well, the Andromeda Galaxy, the very one that was shown here with a telescope, is actually this large. It's just that since it's millions of light years away, it's quite dim. But that gives you an idea of the huge scale of a galaxy. Even though it is 2 million light years away, since it's composed of hundreds of millions of stars, it's huge. And thus would take up a relatively large space in the sky above, right? Because you look at something, you're looking at all these objects that are filling your point of view, okay? Filling the horizons, okay? So I wanted to kind of put that in there as an extra added picture to give you some idea about the scale of the universe and how big galaxies are, okay? All right, so now back to the scale of the universe, but rather thinking about size, which we've predominantly been talking about so far, let's briefly wrap this up by talking about time. So I mentioned the Big Bang, but when was the Big Bang? What is that? How long ago was that? What's happened since the Big Bang? All right, so this is the cosmological calendar. You want to read the book on this and make sure you understand the idea. I asked you some questions in the homework about the cosmological calendar. On the cosmic scale, where the time since the Big Bang is compressed into 1 year, right? So 1 Earth year to kind of make understanding of it. And we can think of how long a month is relative to a year, because it goes 12 months in a year. Creatures we would call humans do not emerge on the scene until the evening of December 31st, all right? So humans, the evolution of humans, millions of years of biological history, right? Humans have been around for a long time. We've had civilizations, cave paintings for at least 50, 60,000 years. We've been around for hundreds of thousands, millions of years as a species, okay? But that would happen late in the evening on the last day, right before the end of the year of the cosmological calendar. So that means that everything has happened before. We are just a few minutes of that last day, all right? Stretching 365 days before us are billions of years of history. Our own planet, right, we have here, our solar system forms in September, okay? So that means our planet is about 3 months old, okay? Well, 4 months old, 3.5 months old over the entire span, right? That means before September, there was no solar system. The sun hadn't started going through fusion processing, producing all the energy it produces today. The planets weren't formed yet. There was just a spiral of dust around the early proto-sun, right? The forming sun. So it means all these months, January, February, March, April, May, June, July, August, that was all before our solar system was formed. What happened before? Well, back in May, the Milky Way galaxy itself, that island of billions of stars of which our sun is just one, well, that was formed in May. That means before May, there was no Milky Way galaxy, because our galaxy is not a first-generation galaxy. There were galaxies that were born, smashed together, were destroyed, left behind remnants that led to our galaxy. So our galaxy is a third-generation, approximately, galaxy. There's been all these, the solar system, the cosmos was forming those billions upon billions, trillions, 10 to the 18 stars out there, okay? 18 zeros worth of stars stretching over the entire cosmos. Okay? And it all started January 1st, where the Big Bang occurred. And we'll get into those very first moments, because it turns out that all these amazing, interesting things happen in the first seconds of the cosmological calendar. In fact, the first nanoseconds, because they happen so quickly. An unbelievable amount of evidence of energy was released, and we have evidence to show that it was. Right? We have all these fascinating telltale signs of the Big Bang. Okay? But again, to get into the idea of just the time that is relevant when we're talking about the entire universe, well, look at this. Look, if we look in December, we can see that vertebrates, right? These are animals that have backbones, like reptiles and birds and mammals, of course, that they didn't form until December 19th, right? So before December 19th, all there were invertebrates, the sponges, the slugs, the corals, insects, right? Early inhabitants in the tree of life. And so I bring this up because it puts into scale that biologists, when they look at fossils, they're looking back just in the last days of the last month of the cosmological calendar. Geologists that can look at rocks that are 4 billion years old are looking back into just the first few months, or the most recent months of the cosmological calendar. It's only astronomers and cosmologists, those that study the origins of the universe, that are actually looking back at well over half, the first half, greater than the first half of history. Okay? Truly prehistory, right? Because this is where we came from. All right. So, thank you so much for listening to this lecture, and look out next week for a video lecture for Chapter